All right, so section 4.3 was titled GCDs and LCMs, right? Greatest common divisors, least common multiples, and we've done half of this section, the greatest common divisor part. Mostly last time we talked about like algorithms, computational ways of finding the greatest common divisor. We're going to do the same thing with least common multiple as we begin today. So to start with, a definition for least common multiple. Come on. Least common multiple is the least non-zero whole number that is a multiple of all whole numbers in your set. So we talked about the word greatest last time being an adjective describing divisor, but it has to be divisor first, right? So divisors are numbers that are smaller than what you're dealing with. The greatest one is still something smaller than what the numbers you started with. Least common multiple has to be a multiple, which means the number itself will be at least as big as the numbers you've started working with or bigger. So least common multiples are generally large or larger numbers, and greatest common divisors are small or smaller numbers. Now, some of the methods that we use are going to feel very similar to the GCD methods, and they are. The first one is actually called the number line method or colored rods. So I actually have a manipulative to show you on this one. Should have got it out beforehand, so sorry. They draw pictures of these in your book. So let me do this. Let me hand out a few of these. So you girls want to take a look at this one. We'll go back here with the three of you guys. I want you to take that one for Destiny and Marissa. One right here for three of you guys, okay? And then we'll do right here for the two of you guys. Oh, I don't know what happened there. And then the back. Here's some. Oh. Okay, so if you can turn around for a second there, okay? Okay, so if you take a look with colored rods, you'll see rods of different lengths, right? They look like blocks. The white one is of length 1. Looks like the red one has length 2. Right, we have 3s. The green is 3 long. And the purple looks like it's 4 long, and we can go from there. So each of the rods has a different kind of length to them, right? So I'm going to draw pictures on my iPad of what you're looking at here. But we're going to try and see how this would work if you were working with the colored rods, which is one of the ways that this is taught in the public schools right now, or in K through 12 schools, right, is with these rods. So these rods have different lengths, and they show multiples. I'm sorry, let me read what I've got. The number line method, or the color rods method, shows multiples of all numbers on a number line or with rods, and the first value at which the intervals coincide is the least common multiple. So we'll do one that you have rods for first, okay? So I want you to get your rods out that are length 3 and length 4. So I think that's the green length 3s and the purple length 4s. And I want you to stack the rods end to end greens and end to end on the purples until you've got the same length, right? So you're going to have, let me choose some colors that are matching yours. So you're going to have 3 here, and it's going to stack end to end, and here's another 3 here, and there's another 3 here, and you're just going to stack them end to end, and you're going to do the same thing with the rods that are the purples that are the 4s. So they're a little bit longer, end to end. And I'd like for you to tell me how many green rods and how many purple rods it takes until they match up lengthwise.
4 green rods and 3 purple rods.
So 4 here and 3 here. And 4 green rods, when they're 3 long each, is the number 12, right? This is 12 long. And then 3 purple rods that are each 4 long is also 12 long. Does that make sense? What that means is that the number 12 is in fact the least common multiple of 3 and 4. Now, you probably knew that one, right? But establishing that fact, or how you can do that from the perspective of the rods, we can do that with any value you wish, as long as we have enough rods to complete the length of it that works, right? So if you were to take the rod of length 4, let's try another one. So keep your purples out for the rods of length 4, and find the ones that have length 6. Somebody tell me what color they are. What color are they? Teal. Okay, so the teal ones, length 6, do the same thing. Stack them end to end until the purples and the teals line up as being the same length. 2 of the what color? Of the teal. So we have, and I think it should be 3 of their purple. Is that true?
Yeah.
Great. So 3 purples, which we did a moment ago. I do not have a teal color, so we're going to go with this funny blue. I know it's not your color, but pretend for a moment that it is. And this is not a great picture, but it looks something like that anyway, okay? So you had 2 rods. They're each worth 6. So this is, again, happens to be the number 12. And my 3 purple rods is also the number 12. So the least common multiple between 6 and 4 is also 12, right? So you can do this with rods. At some point, your rods might not be long enough, like example 5 that I'm going to show you here in a moment. I don't think there's a rod in your stack of length 15. So if you were working with kids, you'd have lots of examples of things that would work with these rods, and they'd make them long enough each time, right, manipulatives to work with. Once you exhaust the size limit and you have a problem like this one where it's 6 and 15, you're going to do it on a number line. So as I draw it on a number line, you can still draw it with rods if you wish, and that would probably be the next step that you'd want to do. But eventually, you would be working with the fact that I don't really need to draw it to know that this is going to extend to a 6. And after the 6, the next place I'm going to be at is 12. And then I'm going to be at, 18. Sorry, that should have been there. 12 right there. And then after my 18, I would be at 24, and I would continue, right? So let's go to a couple more. The next one, what's after 24? 30, and then what's one more? 36. So we would mark out on a number line as evenly as we sort of visually can. Better if we had actually a grid of lengths of 6. So we're sort of either drawing them out or drawing sort of these jumps on this number line. And then for our 15, I'll use red just so that I differentiate it. So the 15 will fall sort of in between my 12 and 18. So here's my 15 mark. And then if I go 15 again, I would end up at 30. And the first place where they coincide, arrows landing would be the equivalent of what's happening with your rods when we stack them end to end. And my LCM would be 30. Okay, so for small numbers, this is a great visual way, either with the rods or with the number line of drawing these out. Obviously, if I had to draw too far of this, it would be annoying. It would not, anyways. We wouldn't want to continue this process indefinitely for really large numbers, right? But this is the first one, the number line method or colored rods. Okay, our next one is going to feel a little bit like one we have seen before, where we list things out. This one is an intersection of sets method. So instead of drawing a picture to represent those values, we're just going to be writing the values out. So we list all multiples of each value, and all is a terrible word. All shouldn't be there. How about many? There's no way to list all multiples of anything. You list out many, lots of them, as many as you need, basically. Multiples, and then you find the least value that the list have in common, because it is the least common multiple. So our example we're going to do is 12 and 15. So when I list the numbers 12 out, I start with 12. And then I do 12 like that. You can either think of that as starting with 12 and then add 12, or starting with 12 and then multiply by 2. But either way, you'd go to 24 next. And then what would be the next multiple of 12? 36. We'll list like 5 of them out, and then we'll see if that's enough. What's after 36? 48. 60. We'll do one more. 72. Okay. And we can continue this list again indefinitely until we need to stop. It doesn't give us a visual, but it does allow us to do a little bit less drawing for it, so that part's good. Same thing for 15. I start with 15, and then what would I have?
45, 60.
And if you're paying enough attention to notice, we get to stop here. If not, and you've listed a couple more out, it's not the end of the world, right? But what we're looking for is the first place where they coincide, the smallest value that they have in common. In this case, it's the number 60. So the LCM, and I don't know that I wrote this notation out yesterday, so let me write it here for you. LCM of 12 and 15 is actually the number 60. We can do the same thing with GCD. On some of the previous slides, I can put GCD and then parentheses the two values, and then it equals something. So you'll see this notation used specifically in another example in a moment, but that's what it's referring to, just the LCM of these two numbers. Okay, so again, this is not a terribly difficult method, but as long as they coincide early enough, it works okay. If they don't coincide for a really long time and we write out these really massive lists, we're going to get frustrated pretty quickly. So it's not great for all examples, but it is an option. The next method works for values that are bigger a little bit better. And it is very much like a method we saw before too, the prime factorization method. So we construct the prime factorization for each number. We've done that before. Step 2 says to choose all prime factors. Now, when we did this for GCD, we only chose the prime factors they had in common. Here we choose all of them, whether they are in common or not. Step 3 is to list each prime number with the largest exponent in any factorization. For GCD, we listed it with the smallest in anything, right? The smallest one. And then step 4 is the same. We find the product. So there's just a couple of pieces where it's different. Here where we do all, and here where we do largest. Those are the key differences for this method from GCD to LCM. Now the nice thing about the prime factorization method, that's not necessarily true about another one I'm going to show you in a moment, is that you can do it for multiple numbers, right? So it doesn't just have to be 2 numbers we look at. We can look at it for 3 numbers or 4 numbers or something like that, and it works really well. So let's take a look at 90, 50, and 20. And I'm going to use the division algorithm that I've shown you a couple of times now, just to remind you how it works. So we divide by the smallest prime number, 2, and I get 45. And what's the next smallest prime number that divides 45? 3. Yeah, 5 will come out in a second. And that gives me a 9. And then I get another 3. Wait, what did I do wrong? 15, sorry. I was already moving ahead for the 9 on the outside. My bad. Okay, 15. There's my 3, and then there's my 5. The 3 and the 3 and 9 right there. Okay. So this is 2 times 3 squared times 5. Is that okay for 90? Okay, we're going to do the same thing now for 50. What will 50 divide by first? 2 to give me 25, and then 5 to give me 5, right? So I'll write it down here. This is 2 times 5 squared. And the last one's the number 20, which will divide by 2 to give me 10, and then by 2 to give me 5. So this is 2 squared times 5. So prime factorization is pretty like rote. You just do exactly the same thing every single time, breaking it down. It always works exactly the same way. It's the part at the end that changes on whether or not you're finding a GCD or LCM. Here we're finding the LCM, least common multiple. So I need all of the factors that are bases. This has a base of 2, 3, and 5. There's a 2, there's a 5, here's a 2, there's a 5. So 2, 3, and 5 are what I have. Even though they don't all have a 2, 3, and 5 in them, 2, 3, and 5 are present in one or more of them. So I include them in my prime factorization LCM method. And then I need the biggest exponent present anywhere in the problem. So what is the biggest exponent on the 2? A 2. I see 2 squared here. What is the biggest exponent on the 3?
2.
Happens to be a 2 as well. And I see that here. And what is my biggest exponent on my 5? A 2. And that's right there. That does not always happen that they all match. They just did here, so don't go thinking that that's a pattern of some sort. It's not. So that's my LCM in factored form anyway. And then my last step is to actually multiply it out. So if you grab a calculator and you were to multiply this out, what will you get? Four times 9. What is it? 900 it is, yes. 900 is the LCM using prime factorization, this method. So I don't know about you, but I would not want to write the number 20 out until I got to 900. Right? That last method would not be a good one for these 3 numbers. It just would not. You'd be really annoyed with me real quick if I told you to do it that way. You'd have to write a very long list. So that would not be a good method for this particular set. The next one also mimics another method that we've seen. It's the division by primes method. You can also use this one on multiple, like 3 numbers in a row, or more than 2 numbers. But you write the numbers in a row. We've seen that before. You divide by the numbers that they have in common, prime factors they have in common. And then you keep doing that division process, right? Divide the quotients. The caveat is that if you have 2 of them at least that still divide by something, you'll still be able to do the division. I'll show you what I mean by that because this example has that. So even if all 3 don't divide by something, but just 2 of them do, you can do that. And then instead of when we did GCD multiplying all the numbers that they divided by together, you multiply all the numbers they divided by plus any remaining pieces together too. So it's a very similar example. Maybe it's the same one. I think I did use the same. No, it's similar. 90, 100, 20. The last one was 90, 50, and 20. So we're going to use our example that's going to feel very much like the last one that we did because the numbers are similar. We're going to write the numbers in a row. So I have 90, 100, 20. And if, in fact, they do all divide by something, I divide them all. So what do they all divide by? 2. So we're going to start there. 2 gives me 45, it gives me 50, and it gives me 10. Now, they don't all divide by 2 any longer, but what do they all divide by? 5. Okay, so 5's next. They all divide by 5. So that gives me 9, 10, and 2. Does that look okay? Okay. Now, looking at the last row here, 9, 10, 2, I do not have 9, 10, and 2 all divisible by anything, correct? I don't. But at least 2 of them are divisible by something, like they share a common factor. What is a common factor between at least 2 of these? The 10 and the 2. So we're going to draw this division. We're going to put the 2 right out here. The 9 doesn't get divided, it just gets dropped down. But the 10 gets divided, and the 2 gets divided. So the place where we stop is still a place where there's nothing in common to all 3 of them. Okay? But not even to all 3 of them, taking 2 at a time. Like we want to get it broken down so that there's nothing in common in even 2 of them at a time. And then the product giving me my least common multiple is all these pieces. So it isn't, like if we were doing GCD, we would have this. Okay, but we're doing LCM, we have all the values on the bottom as well. So my LCM is 2 times 5 times 2 times 9 times 5, technically times 1, though it doesn't change it. 252, 951. 900. Happens to be the same as the value we had for the previous one. It's 900. Any questions on that? Okay. There is a relationship between GCD and LCM, which probably shouldn't surprise you because the last two methods were very similar, but they took different features, right? I used all instead of just the ones they have in common. I used the largest instead of the smallest. Here, I divided, but when I multiplied everything at the end, I multiplied by the values on the bottom as well. There's got to be some connection between these values because the methods are quite similar when I find them. So it looks like this, actually. There is a formula that relates the greatest common divisor and the least common multiple together. And in particular, the greatest common divisor multiplied by the least common multiple is the product of the two numbers that you're working with. And this has to be used with just two numbers. I can't do it with three. So again, remember, this notation is just telling you the greatest common divisor of what? It's not multiplication. It's just the greatest common divisor of the values A and B. This is the least common multiple of the values A and B, and this is really the product of A and B. So why is that nice? Well, it's nice for a couple of things. If you're asked to find the GCD and the LCM of a value, and you did both of them, and maybe you're even asked to find both of them with division by primes, right? If you find one and you find the other, and you're able to multiply those two values together, it should be the same thing that you got by multiplying the values themselves together. It's a good check step. But it also allows you to take a value that you have found and find the other value without going through the work. So that's what's going on in example 9. It says to find the LCM of 72 and 126 using the GCDLCM formula. And we already found the GCD before of this for 72 and 126 in example 4. So I'm going to abbreviate. This is the LCM in whatever order in the GCD. They multiply together, and they're supposed to multiply together to give me 72 times 126. Those are the two values. Now we found the GCD back on example 4. What was the GCD that we found in example 4? 18. So this is actually the LCM times 18 equals 72 times 126. So how could we solve this type of an equation?
Divide the 72 times 126.
Okay, so, all right, so yeah, one way, I mean, it doesn't matter the order in which we do it, but we're going to end up dividing either way by the 18. So you can either multiply 72 times 126 and then divide by 18, or you could reduce this from a fractional standpoint if you wish. That's fine too. What is 72 times 126 and then divide by 18? Remember, it's going to be a larger number that is larger than 18 at least, larger than 76 and 126 too. 72 and 126 as well.
104 at the end, or just 72 times?
What is 72 times 126? We'll start with that.
9,072.
9,072. Okay. And then what is it if you divide by 18? 504. Did that come out this time, Faith?
Yes.
Yes. Okay, good deal. 504. So I did not find the LCM by any method that I just learned. But I did it using the formula that shows the relationship between the LCM and the GCD instead. Any questions on that? Okay. So the hardest part of this section is not somebody saying, find the LCM of this number and this number, or these three numbers, right? The hardest part are going to be the questions where you have to figure out what you're supposed to be finding. So we've got a couple of examples of problems, and they're set up for finding either GCDs or LCMs, but you have to be able to read through them and decide which one am I doing, right? Because if it told you, then it wouldn't really be an application problem. It'd just be the same thing we already did. So our first question says, two bike riders ride around a circular path. So imagine a track if you want to think of a track, a park, something like that. The first rider completes one round, in 12 minutes. And the second completes one round in 15 minutes. So can you imagine? They're both going around the same loop. One of them is doing it in 12 minutes, and they keep going, right? You're going to keep going and keep going. The other one's doing it in 15. They have to start at the same place and the same time. That's a necessary caveat, right? It's like putting our logs, or they're not Lincoln logs, but putting our little colored rods together. They started at the same edge, right? Okay. And they're going to keep going at the same pace, because obviously if they slow down, this won't work either. So there's a little bit of, fuzziness to it, but assuming that they can continue at that same consistent pace. After how many minutes will they meet again at the starting place? Okay, so they might cross paths somewhere else along the road, right, out there and, at halfway point. But the question is, when do they meet again at the starting place? Is this a least common multiple question or a greatest common divisor? You're right. It is least common multiple. Do you want to describe why you think so, Faith?
I was just thinking, in relation to the blocks, you're finding where they meet at the end of it, and it's not just they cross at one point, it's when do they, overlap at that certain point.
Right. So we're doing something repeatedly over and over again. That's a multiples effect, right? There are multiple times they're going around the track, so this will be a least common multiple problem. The fact that we want the ends to match up is like our colored rods. It will end up working with a least common multiple. So I need to find a least common multiple of 12 and 15. That's what this question is telling me to do, and I get to pick what method I want to use, because it doesn't say, right? Because if it said, then they would already be telling you which one it is. So you do get the benefit of choosing your favorite method for these particular problems. You just have this sort of front end of making sure you're picking the right choice. Is it LCM or GCD? So what method would you like to use for the 12 and the 15? Division by primes it is. Nobody's talking to me. I like division by primes, so we're going to do it. All right, what do they both divide by? 3, thank you. 3, and I've got 4 and 5 done here. 4 and 5, what do they both divide by? Just 1, right? There's nothing additional, right? So since I'm doing LCM, I multiply all 3 of these together, the 3 on the outside, the 4 and the 5 at the bottom, and what do I get? 60. And there's context to this problem, so it's 60 minutes. This is 60 minutes. So make sure you're using units when appropriate on the particular problem. So generally, some things to look for, sort of as red flag items for LCM problems, is that you're trying to do things that you multiply together, like you get multiples of. There's a really good example from a movie you may or may not have seen. It's definitely outside of your time frame for your age, but my children have watched it because it's a cute movie. Have you ever seen Father of the Bride? Okay. Steve Martin, Father of the Bride, gets really frustrated about the expenses of the mounting wedding. The mounting expenses of the wedding for his daughter, which is definitely over the top. But he goes to the grocery store and he gets really frustrated because the buns and the hot dogs are not sold in the same quantities. So I don't remember what the numbers were, because actually buns and hot dogs generally are sold in the same kind of quantities, but not always. So imagine that you had hot dogs being sold in quantities of 10, right? They're packages of 10. And you have the buns being sold in packages of 8. Well, I can't just get 1 pack of buns and 1 pack of hot dogs if I want everybody to be able to have a hot dog and a bun as a product, right? Like an item that they're holding, right? That doesn't work. I have to get them to sort of line up like your colored rods, right? It's an LCM problem because I need multiple packages of products. Multiples are showing up, okay? And as a fun fact, I actually had this happen to me personally with hamburger buns and hamburger patties in a store about a year ago. I was doing that for an event that we were planning. So it does happen where products, you're trying to get them to line up and you're looking for how many multiple packs am I going to have to make this make sense. Okay, so that's what you're kind of looking for when it's an LCM problem. There's a couple of ways GCD problems can show up, and so I'm going to spoil the fun for you and tell you, obviously, this is one of those because, I needed one of each of them. So this is an example. Dr. Hands makes cupcakes for her students. It's actually a true fact, right? I've done that before on more than one occasion. She makes 20 chocolate cupcakes and 24 vanilla. She wants to display them on plates with the same number of cupcakes on each plate. Okay? But there's some conditions, and there's one of two ways to do the conditions. One of the ways is the way I've outlined here. Only one type of cupcake on each plate. Isolates the cupcake, so I need a number that will divide evenly into my chocolate cupcakes and a number that divides evenly of my vanilla cupcakes, right? That's why they would need to be on separate plates. The other way to do them is that your plates themselves are all the same. So they can have some chocolates and some vanillas on them, but however many chocolate they have on them, they have to have, like the same number of chocolate on every plate. So if it's 2, every plate has 2 chocolate. If it's 4, every plate has 4 chocolate. But it might also have 2 vanilla or 4 vanilla with it. That's the way that you get things to divide evenly. So those are the kinds of things you'll see measuring up or matching up. So on this one, I need to divide them into smaller quantities, right? So it's a GCD problem because it's asking me to take the number and break them into smaller pieces, not by multiples of packages of chocolate cupcakes or multiples of packages of vanilla cupcakes. Does that make sense? Okay, so we are finding a GCD here of 20 and 24. What method would you like to use? Prime factorization. And you can choose whichever one you like. So if you don't want to do that one, you'll have to. But we'll do it together as prime factorization. So prime factorization takes the numbers and divides them. So 20 will divide by 2. That's our smallest prime. And giving me a 10, which will divide by 2, giving me a 5. And I'm done. 24 divides by 2, giving me, dividing by, giving me, and 3. So this is 2 squared times 5. And this is 2, cubed times 3. Now it's not an LCM problem, so I don't want all the prime factor bases. I just want the ones they have in common. So what bases do they have in common? Yeah, just the 2 as the base, right? They both, one of them has a 5 and one of them has a 3, but they don't both have 5s and both have 3s. 2 is the only one they share in common. And then with GCD, you guys are already jumping ahead of me, we want the smallest value that they have. So it'd be squared. So it's 2 squared, which would be 4. 4 what? Cupcakes. So imagine what this is literally doing. You're creating plates of cupcakes. There's 4 chocolates or 4 vanillas on each plate, right? The number 4 evenly divides 20. I'd have 5 plates of chocolate cupcakes. I'd have 6 plates of vanilla cupcakes. You can also think about putting them like in rows, like if you've ever been to like the donut shops where they put the things in rows, same kind of a thing. They all want the rows to be the same length, right? So 4 chocolates in a row, 4 chocolates in a row, then 4 of the vanillas in a row, and 4 vanillas in a row. Same idea as placing them on the plates. Any questions on that? All right.